Okay, let's get started with AC/DC switch mode power supply design, episode 5. So, where were we? It's been a couple of days. Let's think a little bit. I know at least that I did some research since the last time about, in order to select a transformer, you need to have a specific core based off power rating, like wattage. And in our case, we selected EE25, which can handle up to 30 watt, I think. The primary inductance, the primary number of turns on the windings. Primary and secondary, and then also the was this the auxiliary maybe, and the maybe it was, yes, auxiliary winding. So in order to select a transformer for your design, you need to know this, and you get to that based off of some calculations, which are not that difficult actually. And having slept on it for a couple of days now, I understand a bit more on how you choose a transformer and why it's important. And of course, based on you won't maybe be able to find exactly the transformer you're looking for when you're you calculate out all of these different turns, number of turns on primary, secondary, auxiliary, primary inductance, all that stuff. But I found one that was suitable, I think, and I wrote it down because I found it during the weekend when I was not working with this. And it is, and I think it should be I think it should work, but I need to it's and the funny thing is I found it also last time. So it was basically the only transformer that came up that fit our criteria. So in a way, it's a little bit meant to be, I think. And that's this one, the 7508112349 from Wood Electronic. Power transformers mid OL or M. I guess there's an explanation on that. Oh no, that's the series, okay. It operates between 85 to 265 volts, so it's a universal thing, so it's perfect. I have no, reference to price, but let's say one costs about, maybe I should put this on, now I have it in Swedish crowns, but yeah, 100 crowns is about 10 euro. Let's say. It's not exactly that, but yeah. And then based on volume, of course, you get less than that, but since we're just doing prototypes or basically just a couple, maybe 10, it's still around 94 or 10 euro. So 1 euro per piece. But that's not too bad, I guess. Power rating 26.4, so it's a bit over the 24 that we have, and that's all right. 12 volt secondary voltage rating, which is what we want. Secondary current rating 2.2, which is within the specifications. It's a through-hole component, and I guess for bigger components than this, I mean it's 24 or 25 by 25 millimeter and 17-ish millimeter high or tall. The inductance is 681 microhenry. The standard operating temperature, I guess, -40 to 125, and then the operating frequency is within what we also selected. I think we did 55 switching frequency, so that is all right. So it's a SOIC package. Wait, no. Is it through all component? And it looks like this. Look at the datasheet. And here you can even say or see the turn ratio and how it actually works. So for every 8.75 turn on the primary side, you need 1 turn on the secondary side. So we can use that. It's close to what we are working on. So maybe I can alter that and use this for the turns and then figure out which reflected voltage you should have, if I remember the calculations correctly. Because you assume a reflected voltage, and this you have to balance, but balance the stress between the primary FET and the secondary diode. And it should be around ballpark at 80 volts to about 120 volts, so or something like that. So I put it at 100, which is okay. And I assume 0.5 voltage drop, which we will get to later, right? So this is all assumptions, and then we get a ratio. And based off that, we can see. So if we use the primary and the secondary of this one, 8.75 and 1, then we can, and we also still assume the same forward voltage of the diode, then we can get to what the reflected voltage should be. So we can specify that, and then we of course have to select, you know, the MOSFETs that can handle that, and the clamp circuit. Okay. But since we're learning all of this anyways, this is how we're gonna do it. We're gonna select a component that looks to be, at least it looks to be. So this looks to be within the specifications, and then, yeah, we see how it goes. But yeah, it looks to be perfect for this application. So table shows a typical flyback application designed to comply with these standards, which yeah, I'm not 100% aware of, but it will be fun to read into it. Leakage inductance is 14.7 microhenry. Which, yes, is also good to know. Inductance factor. Yep. And what was this? Switching controller's current mode. Okay, yeah, so basically we have selected the QR flyback controller, which is this one, and then now we can then change from can I copy style of this? Copy format maybe? Copy style, paste style. So the transformer we select is this one. VUT, electronic. Mm-hmm. And then maybe we should redo the calculations a little bit based off of that. So, for example, let's talk about the inductance first. It has a value of 681 microhenry, which is test conditions N1 over 10 kilohertz over. Let's see what our primary inductance was. It was 192 microhenry. LS. Let's see. I did find a nice guide also before. Flyback transformers, coil inductance. What is the inductance? So the inductance of a transformer refers to mutual inductance, the ability of a changing current in one coil to induce a voltage in another coil. Transformer's inductance also includes magnetizing inductance and leakage inductance, which relate to the primary coil's ability to create a magnetic field and a flux that doesn't link the secondary coil, respectively. Inductance is measured in Henry. It's influenced by the number of turns, core material, core geometry. Yeah. So it's representing the efficiency of energy transfer between primary and secondary. So I guess it's capability. So in our application, we came out to this secondary inductance, and then we yeah. So if I understand correctly, we need this magnetic field. I'm trying to like explain it to myself in a better way so I understand why the inductance is important. So if it represents the ability to transfer energy from one coil to the other in order to get this desired output of, what do we have here? Like, okay, these calculations are wrong, maybe, or no, this is correct. Yeah, it's the ability to efficiently or transfer energy from one coil to the other. Then we need this amount of inductance in order to transfer this energy to the other one. I hope that's correct. But that's how I resonate or make a decision that this particular transformer is correct. It just changes the calculations a little bit, perhaps. We know the ratio, or the turn ratio. Okay. Yeah, let's just go with that. No, that's too easy. That's too easy. Selecting transformer or AC/DC design, converter design. Just trying to Google the impact of selecting a transformer with a higher inductance compared to these calculations, if that's all right, or understand the relationship, or like what really is the consequence. Or inductance. Um, I read about it in the weekend. I'm pretty sure that you can select a higher one at least. It's just capability. So it's capability to transfer energy from one to the other. So let's just go with that for now and do something else. Yes, so we're here. We have selected this. We can do the bridge rectifier. I'm curious about that. So what I will do is, because I don't know, I will go Mauser and then bridge rectifier. Bridge rectifiers. Single phase bridge, 3-phase bridge. Yeah. So you got the single phase and a 3-phase. So basically like this. Voltage, current, power. Fewer design costs, less complex design, many application uses, higher power. Okay. But yes, let's just use single phase basic definition. Uses a single alternating voltage. The 3-phase use 3 alternating voltages out of phase with each other. So it requires more wires. It's more efficient for larger motors and heavy loads. We're not doing that. First of all, we're just doing the converter. And then we will see what the actual load is, if it's just some LEDs or something. Application suitable for homes. 3-phase is more industrial applications, large motors. Typically provides lower voltage up to 240, while 3-phase can do higher. So yes, let's start with single phase. Let's just leave this open, or maybe just through hole SMD. How do these even look like? Bridge rectifier, single phase. I assume the forward voltage, Our forward current has to be some margin above our rated current. Maybe above 2.5 then. Peak reverse current. Let's Google is selecting a bridge rectifier for AC/DC design. So I'll just pick up one article that I find and read it and get a sense for why we are choosing these or how. So we know how it works at least. It's basically this symbol for a bridge rectifier. We have a noisy AC signal from the socket, and then it goes through a filter, which we maybe haven't added in that block diagram. But anyways, without that filter, it will still be a noisy AC input signal. Then it goes through the rectification phase, which we use a bridge rectifier. It will strip away the negative portion. That's how I interpret it. It's probably better words for it, which will come in time. But first of all, that's an easy way to just think about it. That it strips it away and it adds it back up here. Keep it simple. So that's what it does. It converts it basically to from AC to a direct current, where it's more pulsed until it goes further. And out the switch, and then eventually a stable DC output. Choosing the correct rectifier depends on several factors, including voltage, current ratings, and the type of circuits. Using a network of diodes arranged in a bridge configuration. Selecting a bridge rectifier, focus on the following parameters. Voltage rating. Ensure the rectifier can handle the peak AC voltage. Current rating. Match the current rating with the application's requirements. Match the current rating. Frequency, verify compatibility with other circuits' operating frequency. Efficiency and power loss. Choose rectifiers with minimal losses for higher efficiency. Application-specific needs. For example, consider a full-wave bridge rectifier for higher output stability, or a three-phase bridge rectifier for industrial systems. And here we already selected a single phase to keep it simple. Popular models and their applications. General purpose, high performance, three-phase, high voltage, specialized. And we don't have to read all of this because we will, make small appliances, LED drivers, and other consumer electronics where space efficiency is essential. So we can start there and look at the general purpose ones. These are designed to handle high power requirements, making them ideal for motors, heavy machinery, and large-scale applications. Compact models such as DB107. And I did research on this also in the weekend, and I remember this component. Bridge rectifier. Okay, not recommended for new designs. Please use not that one. Yeah, but we can choose one of those. So the bridge rectifier is a full wave rectifier, while just using a simple diode is a half wave rectifier. which should be that instead of adding the, the stripped away negative portion of one period and adding it up here, it's lost basically. These rectifiers use only 1/2 of the AC waveform, which reduces their output power and increases ripple voltage. However, they are easier to design and require fewer components, making them ideal for basic circuits, small electronic devices, and battery chargers. So for example, this one, which is just a diode. Also converts this signal then to a DC signal. So the key comparisons are the full wave rectifiers are significantly more efficient as they utilize the entire AC waveform, while half wave rectifiers only use 1/2. Full wave have a smoother DC voltage with less ripple. Cost and simplicity. Half-wave rectifiers are dominating applications. Full-wave rectifiers are preferred for high-power, high-performance systems, whereas half-wave rectifiers are suitable for low-power, cost-sensitive applications. But I would think that selecting a bridge rectifier to cope with a AC signal from the socket is a must. I don't know about using just a diode, but for example, this one, look at the forward voltage or 1 ampere. Oh, it goes up to 1,000 volts. So maybe it's still just as applicable. You would have to select, one of these. So this was 4007. Yes, wow. Okay, but let's just use a full wave rectifier because it sounds cooler. And because of full wave bridge rectifiers. Enough said. Common bridge rectifier models and their ratings, practical use cases. So here the voltage, 1,000, which I guess is good to have. So the voltage we will have will be in DC, or 80 to 265 VAC. That's calculated to DC, which I learned also to be like V in min is V in VAC min times square root of 2. And the same for V in max. This is like DC then. VAC max square root of 2. which should be 95 volts. On this 375. And because of the reflected voltage 100 volts, the max can actually be 375 plus 100 volts. And I think maybe we can look at the design guide here, where we're selecting MOSFETs. No. Yeah, this is where I saw it. I think. Output rectifier. Nothing about input rectifier here, maybe. But yeah. Yeah, so the voltage rating is important, the current rating. Well, voltage rating, current rating, frequency. Peak reverse voltage. Forward voltage. Surge current. Okay, let's see what we have with that. KBU4G M3P. $21 we get in the end. And here was one very cheap. So let's see, bridge rectifier is 35 amps. Sounds a bit excessive, but here, for example, bridge rectifier TBS A30MTP, bridge rectifier 1000 volts, 3 amperes. Quite cheap. 6.5. Low forward voltage, 4 amps. A bit more expensive and a bit different package. What about this one? 4 amps. Bridge rectifier, surface mount glass, passivated fast recovery bridge rectifier. There are a lot of these in stock, at least. RPM. Mm-hmm. I'm curious about these ones. This package looked nice. Maybe that could be something. This I've never seen before. But it's about the same price. It has a lot in stock. Punjit, haven't heard about this before. What about this TBS? This is even cheaper. It's probably pretty good. I would look into that one. These are quite expensive. The bridge rectifier alone, 43 crowns. Okay. What is going on? TBS G4. What about this one? A bit higher current. Peak repetitive reverse voltage. Working peak reverse voltage and DC blocking voltage. RMS reverse voltage, average rectified forward current. Yeah, why not? Let's not make it too complicated. So we are selecting this one. And that's basically what we need to do, right, for that one. I'll just copy that there. To copy style, paste style. So. Because what we need to do, so here we have between 80 and 265 volts. So the reverse blocking, or how to say, the peak repetitive reverse voltage. So the highest repetitive reverse voltage is 1000 volts. So if it's at a maximum of 265 plus the reflected voltage of 100, let's say 500, when yeah, it's positive, it will conduct here then, and blocked here. No, wait. AC in. So it will go like this. Right? And when it's negative here, We need to learn this. So the input, positive, negative, DC output. Here, yeah, I guess. So this would be ground. This would be DC. Yeah, here, plus minus. The voltage drop across resistor. Okay, so in the positive waveform, passing through here, out and across the load, and back in here, this path, and then back to the source. Negative, it would go in the opposite direction, go here, pass through the load, up here, through the diode and back. Yeah, right. So positive house, this is a nice picture, maybe very yellow, but in the positive half cycle, so and it goes down, so the positive one. Yeah, here it looks from maybe the other way. But this way, going through the diode, through the load, and back to the source. And then the negative half cycle, it goes in this direction, or the current flows in this direction, across the diode, goes out through the load, and back again. And this is the tough part, right? When you're designing things that you haven't worked with so much before, you're trying to explain it to yourself that you understand why you select these components. It's very simple just to say or Google and you get an answer like I did here before, maybe here. So I could have used K, yeah, or this one, DB 107 MB 10.5. I chose one, yeah, TBS, but we can look at these ones and see what's so special about them. This one, for example. Bridge rectifier. Low forward voltage drop. Manage your packet, save space on PC board, reliable, robust construction. But it's the same repetitive reverse. What was it? Repetitive reverse voltage. RRM. Output current 0.8. Forward voltage 1.1. IR Was IR? Leakage current, right. Okay. Well, how I understand it is, if it's capable of 1,000 volt repetitively, or continuously, since it's a AC signal, it will continue going this way and then reverse every cycle. So it doesn't damage the bridge rectifier, right? That can't be much more complicated than that. Repetitive reverse voltage bridge rectifier. It indicates the maximum voltage a diode and a bridge rectifier can repeatedly withstand without failing when reverse biased. So choosing a rectifier with VRR rating higher than the expected peak reverse voltage of the AC input is crucial for reliable operation, preventing diode breakdown and thus avoiding damage and ensuring the conversion of AC to DC. Right. So this is the output, right? It's let's say this is V out, and this is 0 volt. So in the positive cycle, it will be current will flow like this, and across the if the load is the C in, then so let's just say it's just a simple resistor, it will go to ground. So that completes that circuit. Same way the other way. Yeah, so the positive cycle here, which then is plus V. And then the negative. Damn. Why am I not getting this? I need to look at this image again. Yeah, so the positive cycle V in is then 265, say. And this is reverse biased. This is forward biased. So it will conduct this way and out in the V out and across the load and back the other way, back into the source again. So in this case, then that would be down here, here, this way, and then back into the source. And in the negative cycle, it will be the opposite way. So current will be flowing in this direction. And yeah, and in that case, it's negative. So it will flow in this direction again, back and up into the load. No. What am I saying? It will still flow in the opposite direction. This way, across the load, back here, across or through this diode, and then back into the source. I need to do more research, learning more about that topic. Okay, but at least we know that this this bridge rectifier will handle it in terms of the voltage. The highest peak voltage here will only be 375 volt plus the reflected voltage from the transformer, I guess. So, yeah. And then the current, we're designing for maximum 2 amps. So, and this one was 6, so we're above that. Okay. Should keep this. Okay. Which one should we do next? Maybe the diode, output diode. It needs to handle 12 volts, right? Selecting diode. I'm kind of jumping a bit ahead. Actually, I could be following this one and going through the MOSFET and everything, but it's fun just to select the components as you go. So we already then selected a bridge rectifier, then we can go and select the output diode, which is also a rectifier. And there, yeah, we need 2 amps at least that we know, or forward current. Yeah, maximum for at least 2 amps. Say 3 amps and above. See what we get. Reverse voltage. It has to handle forward voltage. The lower the better, right? But let's say reverse voltage. Is that so critical though? Like, at that point it's DC, right? Let's look at this design guide again. We'll jump ahead a little bit. Output rectifier. Selecting critical components. So we're selecting this part. Output rectifying diode. First voltage applied to the output diode, VDR, is equal to V out max plus V in max times the turns ratio. Oh. So we need to do some more calculations. You know what, let's go back to here and just check a little bit where we left off. And this is where we left off. We selected determining transformer specifications. This is a bit more of a custom transformer, and that's why I kind of cheated a little bit by selecting one off the shelf based off, turn ratio and output current and everything. So I think it would work for our application, though I'm not 100% sure, so I would need to verify that. But we can move on, selecting critical components, for example, the MOSFET. Which needs to handle those spikes, yes, because of the leak inductance. Yes. So where we are, we selected a transformer, flyback controller, bridge rectifier. Oh, let's do the MOSFET. Let's do the MOSFET. Okay, so we can follow. We'll wait with the diode. We can follow the design guide. The first thing that must be understood is that because selection of MOSFET is difficult to perform based exclusively on a priori calculations, empirical formulas are needed. Ultimately, an actual model is used to verify the extent of the rating that is needed and to determine the MOSFET that must be selected. The following basic items must be examined. Maximum drain to source voltage, which would be here, right? Drain to source. So drain to source. BDS. And that would be then when the switch is, when it's open, when the switch is open and the voltage is VDS here, or there's a voltage VDS here. No. No. I mean, it's both. No. VDS max, the value of VDS max can be determined from the following equation. So VDS max is V in max plus V or, so the reflected voltage, plus the V spike. And the V in max was 200, in this case 264 times this, which should be where root of 2 is 1.41, yes. So that's this times square root of 2 plus 12 volt plus V or, wait, what was V or? Yes, a reflective voltage, huh? Which is, no, wait. They're like the expected voltage output, or the selected voltage output plus the forward voltage of the diode times 30 divided by 6 plus voltage spike. 30 divided by 6. Okay. Yeah, okay, that's winding ratio maybe. V out plus V multiplied by the transformer winding ratio. And then you get this plus the voltage spike. The peak value of the corresponding maximum AC voltage. Because V-spike is difficult to calculate in this example, assuming that a snubber circuit will be added and based on an empirical formula, the value of V-spike is assumed to be 400 volts or less. That sounds to me that a MOSFET with a maximum rating of 837 volts has to be selected. And the drain to source current, it should be equal to 2 times the primary peak current. So it should be twice that, and we had roughly the same peak current, I think, 2.4. No, that was the I out max. Primary peak current was 1.23, so it should be twice that, 2.6 something. Should be twice that. For this, we select the MOSFET with the value of VDS max, roughly equal to 800 volts, IDS value of 5 amps. Okay, so sequentially using this MOSFET in an actual circuit, we measure the values for VDS and IDS and the amount of heat generated to verify whether the level of the rating achieved is good enough, because the lower the input voltage, the longer is the MOSFET on time and the greater is the heat generation due to the on resistance or on losses. Especially in the case of worldwide input AC 85 volt to 264 volt, particular attention is required. A heat sink must be provided as necessary to provide adequate heat dissipation. Excuse me. Excuse me. Okay, maybe I will make another set of calculations here. I need to find a better solution than Miro, where I can draw either draw up or do this in like a Word document or something, where you can actually see the calculations a bit better, the formulas. I would just do table MOSFET selection. Wait, I will take this, duplicate. Edits won't affect any. Oh. So I will do like this so I get the same setup. Yes, this works. So what we have. MOSFET selection. I think it's, even though it doesn't feel like it's too complicated, it's still good to kind of go through and check. So what we need to know is the maximum VDS, abbreviation. Oh, okay. Maximum drain source voltage, VDS, max. And the value, it should be the in max plus the R, which is the reflected voltage, then the V spike, and then put an apostrophe there then. So, comment, assume spike voltage. No, I don't know that point. It's difficult to calculate, assuming that a number circuit will be added, and based on an empirical formula, the value of V spike is assumed to be 400 volt or less. Yeah. And for now, we assumed a VR or VR reflected voltage to be 100. And we know V in max. The VDS max is equal to 375 plus 100 volts plus the 400 volts. VDS max then needs to be at least 875 volts. I don't know if everything is like reasonable, but it says this here at least. I can always Google. Assuming V spike or spike voltage of transformer. As if it were a constant like a rate of voltage, that you're considering a range of possible spike voltages from a few volts to several thousand volts, depending on the situation. Spike voltage of a transformer. Oh. I mean, this is basically so at the switch. I haven't forgotten about my NFC reader, but right now I'm having a lot of fun with this power supply design. So, I mean, if you're looking at VDS then, so like this, VDS, when the switch is on, like when it switches on, it will be these spikes basically, and then, right? So it's here, and they can be between a range of voltages, I guess. Or is it like this? Voltage spike primary, voltage spike secondary. Input voltage. Mm-hmm. Yeah. I'm thinking maybe more of the switching frequency oscillations. I wish I could read a bit more on that, but I will wait. Let's just assume the same thing. So 400, so it has to be, it can be up to that. Then we can look at IDS. Oops. So drain to source current IDS is equal to 2 times the primary peak current. IDS is equal to, I think it was 124 times 2 then. IDS, no wait. Is that correct? I out max at 1.23. Two 2.46 amps. So in this example, they selected 800 volts and IDS value of 5 amps. Yeah, and then of course you would measure VDS and IDS and the amount of heat generated to verify whether the level of the rating is achieved is good enough. Let's look at the one they selected. Okay. I don't think that's... Yeah, it is the same. So it's an N-channel MOSFET with a maximum drain to source voltage of 800 volts. Drain current is 3 amps. And then roughly the same. Not recommended for new designs, but this one is recommended. But yeah, we can look for that ourselves. So we know now it has to be let's see what we find. But it has to be at least 875. Maybe we can select lower. I don't know why. I mean, they specified it here and then they assume 400, but that's still above 800. So current is fine. Select one higher than this, or twice the primary peak current. Okay. So MOSFET. In channel. So the drain to source breakdown voltage has to be at least 900 then. 900. Continuous drain current has to be at least 2.46. So we will select 3 amps and up. And only one channel, yeah. Yeah, we have similar package TO252AA than the one they selected in the example. Let's look at price, in stock active. Quite pricey. But this one was good. Oh. Oh no, wait, this one. The from onsemi. 13K in stock, 22 crowns. This one is way cheaper, but it's not recommended for new designs. That's a legacy component, I guess. I mean, way cheaper in bulks. But yeah, I think maybe we just select this one. It doesn't look like it differs so much. So this one. Let's have a look. So it's this package. Known as the double decawatt package. The larger version of the TO252 package and the surface mount equivalent of the 220 through-hole package. 3 indicates that it has 3 terminals or leads. This package is designed for high power dissipation and is commonly used for various semiconductor devices like MOSFETs and diodes. Yes, but it has what we want, right? At least 875 drain to source breakdown voltage and 5.4 amps, so a bit higher, but I guess it's no problem. 3.13 watt power dissipation. Okay, and this one had 36. 36. Okay. Just want to compare the two a little bit. So, junction to case. Post drain current post. Power dissipation. Yes, seem to be way better. So with a case temperature of 25, 158 watt. Okay, what about here? So it has a lower thermal resistance, so it's dissipating more. Or it's transferring heat better, right, from the junction to the case. 0.79 degrees per watt. And then here, 3.4, and then junction to ambient, 75, 62.5, 40. So power MOSFET maximum ratings. Power dissipation. Power dissipation is the maximum power that the MOSFET can dissipate continuously under the specified thermal conditions. The allowed power dissipation varies with the conditions under which the MOSFET is used, such as ambient temperature and heat dissipation conditions. PD is calculated as the maximum power dissipation for a device with an infinitive heat sink at 25 degrees ambient. PDP, the maximum transient power dissipation, is calculated using transient thermal resistance. Yeah, so it has a way higher power dissipation capability then, and that's how I interpret that this MOSFET can dissipate up to 158 watt under the case temperature of 25 degrees Celsius. Compared to 36 here. Okay. Yeah. But this looks good. We've found it based off browsing through here, Mouser, and yeah. Let's move on. Let's take this one. Selection. I can put in the links too, I guess. So. Oh. Okay, we got the bridge rectifier, the transformer, the MOSFET, the flyback controller. And then we can go ahead and select a diode, I think. I think that's also the next step in the guide. The gate drive adjustment circuit and current detection resistors will be explained in the next one. Yeah, selecting the gate circuit. So this one, I mean, that's also good, I guess. Mm-hmm. Okay, let's read through this. It's just one page. Signal is output from the PWM output pin of the power supply IC. Since an optimal operation cannot be ensured by simply connecting the signal to the gate of the MOSFET, adjustments are needed to be consistent with the circuit and required properties. In concrete terms, the MOSFET switching loss and noise must be optimized. We adjust the on and off speed, rise and fall time of the MOSFET so that the MOSFET operates in a manner that represents a compromise between switching loss and switching noise. Increasing the switching speed reduces the switching loss, whereas the greater the switching speed, creating sharp current changes, the greater is the resulting switching noise. So R5 and R6. These two, when the MOSFET is on, adjust the speed with R5 and R6. R5 10 ohms, R6 150 ohm. When the MOSFET is off, adjust the speed with R5 through the fast gate discharge diode D4. In the discontinuous mode for the current mode, which represents a selected operation, basically no switching loss occurs when the MOSFET is on. The loss occurring during off time becomes predominant. Okay, yeah, but we have a different IC, so it maybe makes sense to look at this component that we have selected. And we can, for example, look at the application circuit. Let's see how it's done here. So it's actually the same on the gate output pin. You have two resistors, one is 0 ohm, and the other one is 15. What does it say here? 150 volt. Okay. I'd have to learn or understand at least that part of the circuits. Gate drive. Inside the gate pin, a totem drive circuit is integrated. The gate drive voltage is 10 volts, which is enough for most of the available MOSFETs. In case of a 1 nanofarad load capacitance, the typical values of rise time and fall time are 117 nanoseconds and 27 nanoseconds respectively. In practice, a gate resistor can be used to adjust the turn-on speed of the MOSFET. In addition to accelerate the turn-off speed, the gate resistor can be anti-parallel with a ultra-fast diode like I or 1N4148 to avoid oscillation during turn-off of the MOSFET. It is suggested that the loop area of the driver through the gate resistor and the MOSFET gate to source and back to IC ground should be small as possible. Right, yeah, it says functional description and component design. Or wait. Oh, never mind. This is IC5QSX. Yeah. Okay. But yeah, we're gonna continue next time. So what we know so far, at least from selecting a MOSFET, the switching MOSFET for this circuit is that we also need to select the resistor here, the gate resistor, in order to adjust on and off times, I guess, or the on times. Adjust the speed with R5 and R6. And here, when the MOSFET is off, we need to adjust the speed with R5 through the cascade discharge diode. Yes. But okay, that's it for today. See you in the next one.